Welcome to the latest episode of the MFG Radio Network's Lunch and Learn, as we highlight some of the latest advances in manufacturing and design, gain insights about the newest products and technologies to move your manufacturing ahead of the competition.
Hello, everyone, and welcome. I'm Elizabeth Engler-Modick, editor of GIE Media's Manufacturing Group of magazines. Our first session is from Sandvik Coromant and CG Tech.
Today's topic is creating efficiencies in your automotive machining right from the start. At Sandvik, we like to talk about safety at the beginning of every meeting. So wherever you are today, know your emergency exits, know the alarm systems in the building that you're in. If you're in the plant, wear the proper protective equipment, of course. Often you'll have an assembly point to meet if there's a reason to evacuate the building. Know what your emergency numbers are. First aid kits, know where they're located. And at Sandvik Coromant, we like to talk about psychological safety. That means we want to include everyone. Everyone's opinion is important to us. Please feel free to participate and drop questions in along the way. COVID-19 is still with us. We're working hard to try to eliminate it. Everybody's following local guidelines. We stay home when we're sick. We wash our hands frequently. We observe physical distancing from one another, cough and sneeze properly, and of course avoid touching our face. All those things are important today. Presenters are myself. I'm Brent Marsh. I work in business development in the automotive segment in the Americas. I'm with Sandvik Coromant. Chris Dingman is with us today. He's a technical support engineer with CG Tech. He'll be talking after I'm done. So in the automotive industry, we know that high volume is key. We know that cycle time, cost, seconds, pennies all matter. And we're in the middle of a shift right now. Conventional vehicles, the very first column we see here is talking about conventional vehicles with internal combustion engines. Okay, that's today's state of things. We've been shifting over to hybrid vehicles for a few years, but today plug-in hybrids are becoming even more popular. And the future state is battery electric or fuel cell electric vehicles, which we often refer to as NEV for new electric vehicles. So what that means is there's a lot of change happening right now in the automotive industry. There's a lot of things being tooled up. New types of components that we've not done in the past. Electric motor housings, new types of gear housings, new types of covers, all types of accessories related to e-mobility. So in the coming today and in the coming days and years, we're going to see a lot of retooling, a lot of new tooling, a lot of new processes being developed. So it's important that we get things right from the very beginning. So at Sandvik Coromant, we have a lot of standard solutions. This is an example of CoreTurn Prime, which is a unique solution, but it's available right out of the catalog. And it involves some unique programming techniques to improve productivity on turning operations. You see here some gear shafts that are being done. But we also know, those of us who have been involved much in the automotive industry, we know that there are a lot of custom tooling requirements, special tools. Here's an example. This is an electric motor housing. It's machining a very high silicon. It's, I think, 12 to 14% silicon content material. It's on a horizontal machining center, so this is a kind of a boring bore finishing type tool, finishing a stator bore. And it's multiple diameters being cut at once, and it's raised polycrystalline diamond tool, and it's a very short cycle time, 6-second cycle time. So simulating this could be a challenge with conventional simulation tools, but not for our friends over at Vericut. They know what they're doing. So the goal is to get it right from the start. If you look at this production environment and look at all of these machines and all of the automation and the floor space, think of the capital that's tied up in this. Think of the process planning that had to happen. What machining operations, what tools do we use, what's the cycle time, how many pieces per hour can we make, what's required, what are our production requirements. All of those decisions have to be made up front. And if you make a mistake, it could be very, very costly. So let's talk about one of our custom solutions. specifically for the automotive industry for machining of aluminum components. This example is called the M5 C90 cutter. It's a combination of a finishing and a roughing tool. So it actually, you merge two tools into one, basically. And let's talk more about this M5 family. The tool that's shown here is actually the finishing only version. We call that an M5B cutter. The C is this cutter plus roughing. So let's take a look at this. I'm going to run an animation that kind of shows the arrangement of these inserts and why it's unique. This is actually a step milling cutter. Each insert is cutting its own path, so to speak, kind of like a rotary broaching tool. The idea is to have no burrs at the end of the day. We design these special for each component, typically. The size needs to be right. Great surface quality, high feed concept, very low cycle time, reduction in cost per part, or cost per unit, we often say in the industry. This is the M5 concept for finishing. So we talked about the M5 C90, which is a combination of this concept plus roughing. So here's the M5C. So by adding inserts around the perimeter of this tool, we can take additional depth of cut. It's designed to take 4 millimeters depth of cut, but it can go beyond that actually because there's a safety factor built in of about 2 millimeters. So it produces that same high quality surface finish that the M5B, which is the finishing cutter, and it produces no burrs, and there's never any need for adjustment on these tools. Fixed pocket, easy to set up. Traditional processes typically involve at least 2 cutters, sometimes more. So you'll have a roughing operation, and perhaps it's taking 3-4 millimeters of stock, and then you'll have a finishing operation that may be taking less than half of a millimeter, maybe a quarter of a millimeter of stock for finishing. What we've done is merge these two tools into one. With the traditional process, each insert is on its same location, axially and radially. So each time each insert goes into the cut, it's taking the same amount. This is their feed per tooth right here. It's taking the same amount of material each time. And when you get to the exit of the component, that's where you have the opportunity to fold over this burr right here. That's the problem with the traditional process. With the M5B and C process that we've been talking about, each insert cuts its own path. And the feed rate is governed by the final insert. It's basically a high feed insert. It can take a tremendous amount of feed, but its axial depth of cut is very, very light. So there's no burrs, and the material is shaved. And when it exits the cut, it's a nice clean cut. That's the key to this type of tool. So we talk about the process having roughing and finishing capability. This blue ring right here, these are the face inserts. They lay down on the face. They do the final finishing. The insert in the green band, these are on the tangentially mounted on the perimeter, and they take the roughing. So you can see this down in the corner right here is how that's a good indication of how they're arranged. This insert being the rougher right here and having that, let's say 4 millimeters plus depth of cut capability from here to here. But this insert is doing the final finish pass to make the final finished surface right here. Here's another look at it. What you see is it leaves this type of corner. If you machine to a 90-degree corner, you're going to get this at the bottom, this stair step. Sometimes that's not acceptable, so it would require a different type of cutter. There's also concerns that you might have some clamps in the way for the component fixturing, or you might have a feature on the part itself that would be in the way. So that's where the people at Vericut come in, because they can detect that ahead of time and you can plan around it accordingly. So we have an example here of a component part. It's a cylinder head. It's for a racing engine, actually. And the machine that's doing this does not have the capacity for a large diameter cutter that would cover the entire surface of the part. Okay, so you'd have to have a much bigger cutter to go across in one pass. Instead, we're going to do this in a U-shaped pass, kind of like a picture frame. We're going to go around the perimeter of the part like this, and then it's going to come up through the middle and do a finish pass, and this cutter will be large enough to cover this combustion face surface without any seams in the operation. So just to recap, there's the priorities in automotive production are increasing output because we have typically very high volume machining, and cost per unit is very important. Pennies matter because you're making hundreds of thousands, if not millions, of components. So it's very important to control cost. But those things being said, we must concentrate on planning the production properly in the beginning. Get it right from the start. That's why we work with Vericut. That's where they come into play. They have the ability to analyze the process before you ever cut a chip. So that being said, I want to exit and hand off to Chris and let him pick up from where we leave off. Thank you.
Thanks for that introduction, Brent. As he said, I work for CG Tech Vericut, and our motto today is to do things right the first time, every time. I'm going to give a demonstration here about how Vericut should be used in your process and why you need to use it in your process of proving out jobs on the manufacturing floor. So I want to talk a little bit too, have us think about what are some major challenges that manufacturers have when they're proving out jobs on the machine, the first run part. So scrapped parts, redos, do-overs, this tool doesn't run the right speed, or there's a cut that I missed, or maybe someone just has a question, so they need to be confident in what's going to happen. They're going to stop, go back to the programmer, and ask what's going on. These are some of the solutions that we can give you with Vericut. First and foremost, with our simulation, our verification, we can detect potential catastrophic collisions, travel limit warnings, things that would cost you money, cause a major shutdown, scrap, things like that, and also, affects the safety of the machinist as well. Vericut's going to help you boost your manufacturing efficiency. You're going to extend your tool life, so you're going to spend less in tools, and you're going to increase the capacity at the machining level, which means you have more time to let your machine make money for you. Have you ever had anybody ask you, why does it take a week to set up a part that's only going to run for an hour or two? Some people, it's hard to understand, why is the process so slow? So let's take a look. What does this guy look like he's doing? He's standing at a CNC machine, and he has his hand on the feed override dial on the machine control. He's slowing down the machine. Now, why would a machinist want to do this at the beginning of a run on a machine? Well, they're worried about catastrophic things happening that will cause a stoppage. Crashes, banging into fixtures, even worse, machine parts colliding with one another. That can destroy your machine potentially. So these are all things that Vericut can easily find before you even get to the level where you're at the machine. And the idea is to, in your process, to shorten this prove-out time. So this is like, some people call it the normal process. I'm going to call it the old process. Okay, so you have kind of your engineering side where you are, your CAM is programming and then outputting through a post processor to create the NC code. It's taken then to the prove-out level at the machine. There's walkthroughs, slow down the machine, do that kind of thing. Find issues that need to be changed, call somebody, take it back, rework it, fix that issue, back to the machine again, and this process happens over and over sometimes. So instead of calling this the normal method, I'm going to call it the old method. And if you are using this method, it's pretty much obsolete with VeriCut. So let's put VeriCut into the equation now. So VeriCut's going to be down here. It's going to be after you've created the NC code, but before you go to the machining area to prove out your program. The idea here is that somebody, like the engineer or programmer who is, offline from the machine, can do a virtual prove out and find issues that are going to occur potentially in the NC program, resolve the issues. If they need to be reworked, that person can make the changes, run through VeriCut again, and all this time when that's happening, instead of the machine sitting and waiting, it's producing parts. So you've removed that wait time out of the machining process. So when you have a clean program, then we go to prove out. Prove out is much shorter. The machinist is more confident in what's being given to them. And you see the capacity here for machining has gotten larger, and there's more room as well out here. Time is money. If you want to make things even more efficient, we also have an optimization product called VeriCut Force. And what we can do with that is adjust your NC program to be more efficient with its material removal, which will in turn shorten the time, increase tool life, and make a safer program. So what do you get in VeriCut? Here's typically what you're going to see in VeriCut when you're running a simulation. You have a view that has the machine, where you can see the machine parts moving. Your NC code might be on display as well, so you can see where you are in the program. And then you want to have another view where you can see the workpiece that's being created. Setting this up is fairly easy. First and foremost, if you have one of our CAM interfaces, you can output a lot of data that you've already configured in your CAM system directly to VeriCut, which is a great time saver. But outside of that, the items you need are the same things that you need on a real CNC machine. You need a piece of stock. What are you going to machine? You need fixed string to hold that. You need tools to remove material and an NC program. With the tooling, smart tools can be imported from the cloud or from online. And what we mean by that is it's a model of the assembly of the tool already put together, already configured for VeriCut's use, and there may even be some metadata that goes with that, like feeds and speeds and so forth. So like in each tool that runs, VeriCut not only is checking for its typical errors and things, but there's tooling related errors that can happen as well. So when you got tools that are not used properly, such as going too fast, or it's engaged in material but the spindle is not on. Another popular one is tap tools. If your speed and feed doesn't jive with the pitch of your thread that you're trying to machine, VeriCut's going to know that, and it's going to tell you something's wrong. And tooling will also contain the values that are used in our optimization, which I'm going to talk about here in just a moment. Here's an example of the M5C90 cutter that Brent was showing you earlier, what it would look like in VeriCut after it was imported into the VeriCut tool manager. And as you can see up here on the top, is they have several different methods for importing tooling if you're not going to build the tooling from scratch in VeriCut. Step 2 in the process is to run VeriCut. Pretty self-explanatory, but you don't have to sit there like this fellow and watch it run the whole time. You could minimize this, put it in the background, go work on something else. Makes you more efficient as a programmer or engineer. You're not wasting time sitting there watching VeriCut run, and come back and review what happened. So at this stage, when you're going to review what happened, here's another shot from VeriCut showing us we got the workpiece over here on the left, and the tool swings up and collides with the machining table. When that happens, and when VeriCut sees that happens, it gives you error messages, okay? Even better about the error messages, when you want to review what are those error messages related to, when you click on them, they link you directly back to the line of the NC code where the issue occurred. And lastly, you can have the option to document your process. VeriCut has configurable report templates that you can set up a la carte how you would like it to be, and there is a lot of different data that is collected in VeriCut that you can output to these reports. For example, how long did a tool run? How long was a tool cutting air? If you're thinking about efficiency and things like that. After the documentation process goes, if you like being paperless, we also have a reviewer. Cam set up on the left. Most of the time this is what you see. Maybe there's a little bit more fixturing, but ideally there's a fixture model. There's your workpiece that you're making toolpath to, and maybe it shows your tool in there so you can see what's going on. And you run the little replay in your CAM system. Hey, everything looks good. I don't see any problem. Are you really sure that that's okay without running it in Vericut? Because if you do run it in Vericut, you'll find out that the column that spindle is mounted to collides with a table as it comes down the machine on the part. That's not good. That'll cost a lot of money and a major work stoppage. So ideally, this tool needs to be longer. That would be the fix for the programmer or the setup person. You're also creating a machined model while you're going through this. So why not compare that model to what your intent was when you wrote the program? So you can give Vericut a model of the cut intent or the finished part for the operation, and it'll compare the cut stock model to that and has the ability to show you the differences where you've either taken away too much material or left material on the part. You control the tolerancing that you want to use when you're doing that. Useful information so that if you have bad cuts or bad programming, you can go back and fix it before you scrap a part on the machine and cause a work stoppage. And multiple setups. I have a part that I'm running, and it's going to be on 3 different machines, stage 1, stage 2, stage 3. We don't have to create 3 separate Vericut projects to do that. You can actually put multiple setups in the same Vericut session. And Vericut will automatically move the cut stock from one setup to the other as the process is playing through. As I said, cut history saved between setups. So if I was to evaluate something on the part and I wanted to know what tool cut a specific feature on the part, I could click on that in Vericut, and it could go all the way back and tell me that that was created by tool 5 and setup 1. There's a history that follows through all these setups and stays with the part. We call it our smart part technology. Very useful down the road. So I've done my simulating, done the verification process. Even though you've made collisions and things go away, clean program, there's hidden missed opportunity in terms of how your tools are being used. So we have Vericut force optimization. Our force optimization is a physics-based optimization method, and what that does is it will change your program's feed rates to try to help you achieve a constant chip load for each tool. The idea being that each tool that is built by a manufacturer is meant to run usually within a specific range of speeds and feeds. Vericut's force can predict what the forces are against the tool, which is what this little middle area in the chart is, where you can see potential problems, while at the same time you can set limits and say the chip load that I actually want to achieve, which might be up here where I have a limit line set. And the feed rate varies usually at the end. So ideally, we want to move our material removal rate or our chip load, increase that, and have a more constant chip load throughout the program. And at the same time, we want to avoid problem areas like those. So those are areas that we need to cap off or reduce to save your part, tool life, etc. In the end, you'll have faster turnaround because you'll have a shorter time that's consumed by running the part. You'll have more time to make your own parts, so possibly less outsourcing. And the tool breakage, tool life, that is greatly changed because now you're running tools the way that they're intended to run. So typical NC motion on the left, we have a motion of this tool going upward, up a slope. And you see there at the very bottom, that blue arrow, it's programmed at 45 inches per minute, constant feed rate from your cam system. Most cam systems are something kind of related to this or similar. On the right would be an example of how we optimize this. So notice on the left, constant feed rate, but then if you look at the material that it's removing below, it changes constantly, which means we have room to change our removal rate as we're changing with the amount of material removal. So Vericut is going to break up your feed motion and adjust it to try and keep the chip load as consistent as possible throughout your NC program. It never changes the actual trajectory of your tool path. We're just breaking apart motions into smaller motions so that we can adjust feed rates. While you're calculating that best feed rate potentially for your tool by using the recommended ranges from the manufacturer, you're also setting limits to push to get greater efficiency and do better. That's all related to the chip thickness value that you want to achieve. But then you can also set limits for yourself so that you don't push too hard. You don't exceed the limitations of the tool or the machine and cause a problem or a bad part. So you can limit yourself by the forces on the cutter, which Vericut force can predict. It can also predict tool deflection. So if you have excessive tool deflection in different areas, that is, you can choose to have Vericut do an adjustment there to try to minimize or remove that problem. Spindle power is also calculated, and all this information is stored in Vericut. Vericut always knows. If you'd like to know more about us at CG Tech, check us out at cgtech.com. That concludes my part of the presentation. We thank you for joining us. Any questions?
Thank you so much, Brent and Chris, for that insight. Why is the M5C90 cutter a concern for collision avoidance different than a standard cutter? Perhaps, Brent, you want to weigh in?
Yeah, that would be in my category. The M5C90 cutter, as I pointed out in the beginning, it has roughing inserts around the perimeter, and they're at a larger diameter than the finishing inserts. And then each finishing insert is in a stepped configuration. So they radially move closer to the axis of rotation of the cutter until you get to the final finishing insert. And it's the closest one in. So there's a few millimeters difference between the OD of the cutter where it begins roughing and the ID of the cutter where it does the final finishing. Therefore, the cutter has to overhang the workpiece slightly. And so there could be a concern about a feature on the part, like a boss or a wall, something that might be in the way on the component itself, or there might be a clamping element in the fixture that might be in the way, or a locator or something like that. And so therefore it's helpful to have the Vericut software to run through first, especially if you're concerned about any of those collisions, just to make sure that you're not going to hit any of those clamps or any of those surfaces. So yeah, that's why it's so good to have Vericut.
Great. And I think we got time for one more. Cosmin wants to know, how do you calibrate the tool pressure based on the machine? Small tools have very little load on the machine. Brent?
I'm assuming, is this question for Chris or for Brent?
They didn't really address, so if Brent or Chris, or we can always reach out to Cosmin afterwards with an answer. Vericut Force.
Vericut Force, good question. Okay, so with Vericut Force, what we have is you select the material that you're machining, and you also define the properties of your cutter, like the flutes, the rake angle, both axially and radially. And with that, Vericut Force can predict areas of high forces being projected against the tool, which helps you point out different areas that need to be addressed or possibly need to be addressed in your program.
You can find more Lunch and Learns plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcasts, or on our websites at todaysmedicaldevelopments.com aerospace manufacturing and design.com, and evdesignandmanufacturing.com.